Hi everyone, I'm Japoo and I just finished my freshman year of college. I took AP Calculus during my senior year of high school, and today we're going to be talking about the product and quotient rules. You can find a copy of the worksheet that I'm about to do as well as the answer key in the description below if you would like to follow along with the video. And just a forewarning, we are not proving either the product or quotient rules today in this video. We're just practicing the application of both of those rules. The product rule and quotient rule can be proven using the limit definition of the derivative, but for today's video, we're just going to accept both of these rules to be true. So for our first rule, I'm going to talk about the product rule. We use the product rule for things that are products, two things multiplied together, and you can switch which part of the product you want to take the derivative of first and which one you want to keep the same first. So you don't really have to memorize this specific formula per se, just understand what it means in different problems. So if we have two components, here we have f of x and g of x. As you can see, we keep one part the same, so we keep f of x the same in the first part of the sum, and we take the derivative of g of x, and then we take the derivative of f of x while keeping g of x the same. The other rule that we're talking about today is the quotient rule. And we use the quotient rule for things that are quotients or fractions. I would recommend just straight memorizing the quotient rule. This is the only way I've seen it done, and it just makes all the problems easier if you memorize it. So there's a little saying that I use to memorize the quotient rule, and I find that it really helps. The saying is low D high minus high D low over low low. And I'll explain that. So as you can see in our example fraction or quotient, we have f of x over g of x. So f of x is the high component of the fraction and g of x is the low component. So in low D high minus high D low over low low, as you can see, we first keep low the same, so we keep g of x, and then take the derivative of high. So the derivative of f of x minus high, keep f of x the same, times d low, so take the derivative of g of x over low low, which is just g of x squared. To use both the product and quotient rules, you have to make sure that both things in the product and quotient are the same. We will have a couple of examples where it seems like we should use either the product or the quotient rule, but we actually do not have to. So our first problem on this worksheet is where we need to use the product rule. I like to underline the components of my product to kind of differentiate them and keep track of what I've taken the derivative of and what I've kept the same. So, as per the product rule, we're going to keep the first component the same. So we're keeping x to the fifth the same, or x to the fifth the same, yes. And we're going to take the derivative of the second component. So we're taking the derivative of 3x squared plus 2, which gives us 6x. And we find that derivative through the power rule. If you're not familiar with the power rule or trig derivatives, which is another set of derivative rules that we use a lot in this worksheet, I would recommend that you stop this video and check out our previous videos where we discuss trig derivatives and the power rule in more depth, just to get a better understanding of those two things. But to recap what the power rule is, basically when you're taking the derivative of a variable that has a power with it, you bring down that power and then subtract 1 from the power. So in this case, we bring down the 2, multiply it by the 3 since the 3 is in front of the x already. So we get 6x, and then subtract 1 from 2, giving us 6x to the power of 1, which is just 6x. And now we're going to take the derivative of x to the 5th and keep 3x squared plus 2 the same. So again, it's the same power rule that we're using, that we just used. So we bring down the 5, giving us 5x, and then subtract 1 from 5, giving us 5x to the 4. And I underlined everything so you can tell where I took the derivative of a specific component and which one I kept the same. So this is another product rule problem. I actually switched which one I took the derivative of first in this problem. So I took the derivative of the first component, 3x plus 5 first, which gave me 3. And then I left e to the x, which is the second component, the same. And then this time I kept 3x plus 5 the same and took the derivative of e to the x, which is just e to the x. And I did forget to underline in the problem which components go with which, but there should be 1 underline under 3x plus 5 and 2 under e to the x. Now in number 3, you'll see that we have a square root. And I recommend turning that square root or any other kind of root that you might have into a power, just because it makes it easier to use the power rule. So the derivative of square root of x, or x to the 1/2, is 1/2 x to the negative 1/2. And I'm going to go ahead and underline the previous problem. And then we're going to keep ln of x the same. And then we're going to keep square root of x the same and take the derivative of ln of x. And the derivative of ln of x is 1 over x. Now, for most of these problems, I didn't simplify. However, in this one, I decided to. That's just, whether you have to simplify or not just depends on like the rules of whatever test or assignment that you're doing. So to combine the first part of the sum, I'm just going to bring x to the negative 1/2 back down to the denominator, and then combine square root of x and 1 over x. Square root of x over x can simplify to 1 over square root of x. And then to get a common denominator to add those two fractions, I multiplied by 2 over 2, which gave me ln of x plus 2 over 2 square root x. All right, and now we have our first problem with the quotient rule. Again, think of the little saying low d high minus high d low over low low. Memorizing that will make this process much easier. So the derivative of h of x is low, so x minus 2, times the derivative of high. So this is a trig derivative, which you just need to memorize. So you'll get x minus 2, which is the low, and then derivative of high, which is cosine x. And then you'll have minus high, which is sine x, derivative of low. And in this case, the derivative of the low component is 1, so that's just understood, over low low, so over x minus 2 squared. In both the product and the quotient rule, be really careful about your parentheses. If you omit a parentheses where it's needed, you could get the problem wrong. So I recommend putting in parentheses for clarity and so you can avoid mistakes. This next one is also a product rule. So we're going to have low 1 plus e to the x times the derivative of high. This is another trig derivative. And so the derivative of inverse cotangent of x is -1 over 1 plus x squared. Minus high, which is just inverse cotangent of x, times the derivative of low, which is just e to the x, over low, which is just 1 plus e to the x in parentheses squared. Notice how I put all of my components in parentheses to make sure that I didn't make any mistakes and that my answer was clear. You could simplify any of these problems further, especially the quotient rules. I just chose not to because the worksheet instructions didn't ask for that. And simplifying these would be a little tricky. So for number 6, we see a fraction, which makes us immediately think to use the quotient rule. However, if you look at the high portion of the fraction, you see that there's no variable involved, which means that you can actually manipulate this equation so that you only have to use a power rule. We want to use the power rule just because it's easier to use and then also easier to simplify. So since 14 is a constant, we can manipulate this equation to make it 14x to the -3. And with that, all we have to do to find the derivative of f of x is a simple product rule. We bring down the -3, and so then 14, which was already there, the constant, times -3 is -42x, and then we subtract 1 from -3 to get -4, which gives us -42x to the -4. We can further simplify that or write that in a better way by bringing the x to the -4 into the denominator to make that exponent positive, giving us -42 over x to the 4. Now, this number 7 is just a basic quotient rule, and you can see the difference between number 6 and number 7, since number 7 does have variables in both the top and bottom of the fraction. So we're going to start off just low d high minus high d low over low, right? So we're going to keep low the same, x squared times high, times d high times the derivative of the high component. And whenever you have a number to that's exponent is x, like you know the number, but the exponent that it is to is unknown, there's a specific formula that you use to find the derivative for that. So say you have a number to the x, the derivative would be, for some reason I could not write the number 2 right here, but it should be x squared. But anyway, the derivative of that would be the number to the x times ln of the number. So in this case, we have 3 to the x, and the derivative of 3 to the x would be 3 to the x times ln of 3. So that's the derivative of the high. And then we're going to say minus 3x, keeping high the same, times d low, derivative of the low, which would be 2x in this case, over x squared squared. And I just went ahead and simplified that to x to the 4th. Now for number 8, you'll notice that we have pi squared times secant x. And that seems like it should be a product again, but since pi squared is a constant, we are not using the product rule in this case. And we can instead just use the trig derivatives to find the derivative of secant x. So we'll have derivative of f of x equals pi squared, keep that the same, and then the derivative of secant x is secant x tan x. And now we're moving on to the second page. So number 9 is, see, it looks like a fraction, so it seems like we should be using the quotient rule. However, since the denominator does not have a variable in it, we can actually manipulate this equation so that we only have to take the derivative of a trig function. So, since 1/7 is a constant, we can pull that out in front of inverse sine and get the equation 1/7 times inverse sine of x. So our final derivative would be 1/7 times square root 1 minus x squared, since 1/square root 1 minus x squared is the derivative of inverse sine. Now, if you did the quotient rule on this question, or if you did the product rule for question 8, it technically would not be wrong. But since the derivative of any constant is equal to 0, doing the product or quotient rule in instances where you don't necessarily have to would make your answer much more complicated, and you would have to simplify to get to the answer that I have. Now, moving on to number 10, we see that it's just a simple product rule. So we'll go ahead and underline the components of our product, and then we will begin the derivative. So we're going to take the derivative of the first part. So take the derivative of square root of x plus 1, giving us 1/2 x to the negative 1/2 power. And then we're going to keep x minus cosine x the same. And for the next part, we are going to keep square root of x plus 1 the same, and we're going to take the derivative of x minus cosine x, which is 1 plus sine x. So again, very straightforward product rule. Number 11 is a little bit more complicated because you see that we have a product, except this time we have 3 components of a product. We have 3 things being multiplied. So I like to call this the triple product rule. I've never seen a problem like this on a test before, but if you follow the product rule, you will be able to do any kind of product problem, whether it be 2 products, 3 products, or 2 components, 3 components, etc. Basically, what you have to do is keep 2 of the components of the product the same, and then take the derivative of the third one. And then do that 3 times, alternating which component you take the derivative of. So we'll say that x plus 4 is the first component, 3x minus 2 is the second, and 2x minus 1 is the third. So, to find the derivative of f of x in this problem, we're going to take the derivative of the first part, so we get 1 because that's the derivative of x plus 4, and then we keep the second and third parts the same. So we keep 3x minus 2 and 2x minus 1 the same. And then we're going to take the derivative of the second part. We're taking the derivative of 3x minus 2, which is 3, and keeping the first and second part the same. So x plus 4 and 2x minus 1 remain the same. Finally, we take the derivative of the third part. So the derivative of 2x minus 1 is 2. And then we keep the first and second parts the same. So we keep x plus 4. And we keep 3x minus 2. All right, so as you can see in this problem, we have both a product and a quotient. I like to think of this problem as a product within a quotient. So the general idea that we should look at this problem with is we should look at it as a quotient. It's just that the high component of the quotient is a product, so we're going to have to use product rule to find the derivative of the high part. So if we just follow the saying low d high minus high d low over low low, we'll just have e to the x for low. We're keeping that the same. And then as you can see, I'm going to start bracketing. I bracketed off what's going to be where we need to use the product rule. To find the derivative of the high component, we're going to have to use the product rule. So again, we take the derivative of the first one, or take the derivative of one of them and keep the other the same, and then take the derivative of the other one and keep the first one the same. So in this case, I'm going to take the derivative of x to the 4 first, giving us 4x cubed, and I'm keeping ln of x the same. And then I'm going to keep x to the 4 the same while taking the derivative of ln of x, which gives me 1 over x. And then we just continue on as usual. But as you can see, we had to do product rule while we were doing the quotient rule to get to our derivative. All right, and we're just going to keep going. So now we're going to keep the high the same. So write x to the 4 ln x, keep that the same, and then take the derivative of low, giving us e to the x. Then we have low low, so over e to the x squared. Now this problem is the same idea, has the same idea as all the other problems we've done on this worksheet, except we have to add an additional step. So dy over dx basically just means that you need to take the derivative of y. And then the vertical line and the x equals 2 means that after you've taken the derivative of y, you have to plug in 2 for every x in the derivative. So our first step is just taking the derivative of this function. And as we can see, it's a fraction. So we're going to use quotient rule since we have variables in both the top and the bottom of the fraction. So following the saying low d high minus high d low over low low, we're going to keep x squared plus 1 the same while taking the derivative of the high. X cubed minus 2 gives us 3x squared because of the power rule. And then we're going to keep the high the same. So keep x cubed minus 2 and take the derivative of the low, giving us 2x. And then we put that all over low low. X squared plus 1 squared. Now, after we've found the derivative of y, we're going to plug in 2 for every x that we see in the derivative. And so if you plug in 2 correctly, you'll eventually get these numbers here, 5 times 12 minus 6 times 4 over 25. Which simplifies to 36 over 25. And that is your final answer. So again, that problem was exactly like all of the other problems we've done, except after you take the derivative, you just have to plug in a number so that for an answer, you get an actual number. Now this problem is almost the same as number 13 in terms of steps. You see that we're provided with some givens in the problem, g of 4 and derivative g of 4. The derivative of g at 4, excuse me. We use that later when we are actually plugging in 4 into the derivative of x, or f. But first we must find the derivative of f before we do any kind of plugging in. So here we're going to use the product rule since we have g of x times square root of x. And we're going to keep one the same, take the derivative of the other one, etc. So we're going to keep g of x the same and take the derivative of the square root of x. And then we're going to take the derivative of g of x, which is just written like that, and keep square root of x the same. After we've done that, we're going to plug in 4 for every x we see in that derivative. That's going to give us g of 4 times 1 over 2 square root 4 plus derivative of g at 4 times square root of 4. If you wanted to skip that step and just go ahead right into turning that into numbers, you can do that. So now we're going to have g of 4. We're going to replace that with 1, and that we know that because it's given to us in the problem, times 1/4 plus 2, and we know that the derivative of g at 4 equals 2 because that's also given to us in the problem. And we're going to multiply that by 2. And that whole thing is going to give us 4 1/4, or 4.25. Now for this last problem, we need to find the equation of the tangent line at a certain point. In order to write an equation for a line, you need to find a point, and you need to find slope. So we're already given the point in this case, and to find the slope, all we have to do is take the derivative of y and then plug in the x value of our point that we are given. So it's basically the same as the 2 previous problems that we just did. Find the derivative and then plug in a value for x. And then there are a couple of other steps after that to write the actual equation of the line. So here we have another product rule, 4x plus 2 times cosine x. So what we're going to do is take the derivative of 4x plus 2, which gives us 4, and keep cosine x the same. And then we're going to keep 4x plus 2 the same and take the derivative of cosine x. Since the derivative of cosine x is negative sine x, I've gone ahead and replaced the addition sign that's normally between 2 parts of the derivative when you're using product rule, and put a minus sign instead of an addition sign. Just moving that negative over. Now that we have the derivative of y, we can plug in 0 for x. So we have 4 cosine 0 minus 4 times 0 plus 2 times sine of 0. For reference, cosine of 0 is equal to 1 and sine of 0 is equal to 0. And that's just based on unit circle stuff in trig. After we plug this in, we're going to get the slope of this line at a specific point, the point that we've been given, and the value that we've come up with is 4. And now we're going to write the equation of the tangent line at this point. So it's really easy to write an equation for this kind of line with point-slope form. Point-slope form is y minus the y-coordinate equal to slope, or m, times x minus the x-coordinate. So we're going to go ahead and do that, write that equation using the point that we were given and the slope that we just found. So y minus 2, the y-coordinate, is equal to 4, which is the slope, times x minus 0, which is the x-coordinate. And that is our answer. So we've addressed a couple of rules in this worksheet in addition to the product and quotient rules. We've come across product rules, trig derivatives. One really important rule that we did not discuss in this worksheet is the chain rule. And if you're looking for a video on that, we have that one uploaded too. So go ahead and feel free to check that out if you're at all confused about the chain rule. We also have a Discord server, and the link to that is in the description below. On that server, we can address any calculus or math ACT questions that you might have. Just send a question and one of us will answer it and help you out. Thank you guys so much for watching. I hope you enjoyed this video. And if it was at all helpful, please give it a like and subscribe to our channel. Thank you.